Welcome to this calm space where we're going to step away from the dense, kind of intimidating textbook equations for a bit and simply explore the conceptual heartbeat of electrical circuits in this explainer. If you've ever felt completely overwhelmed by a maze of wires and formulas, you are in exactly the right place. Today, we're taking a really slow, focused approach to understand the true fundamentals.
So, take a deep breath and let go of that looming exam anxiety. Have you ever actually paused to think about that invisible energy constantly coursing through the laptop or phone you're literally using to study right now? Well, we're going to look at how that seemingly chaotic electrical energy is tamed, managed, and directed. Because, it's not magic. It's just beautifully organized physics.
Okay, let's dive right into this. Any complex electrical network, no matter how massive or confusing it looks on a schematic, is fundamentally just a combination of basic components working together. An electrical network is perfectly defined as the interconnection of basic components like sources, resistors, inductors, and capacitors. It's a remarkably simple, elegant building block system.
Let's start our gentle journey with number 1, resistors, opposing the flow.
The concept here is absolutely straightforward. Resistance is simply the property of a circuit element by which it opposes the flow of current. Think of electrical current like water rushing through a pipe. A resistor simply narrows that pipe, intentionally slowing the flow down. It's a deliberate, controlled bottleneck that keeps the energy from rushing through all at once.
Notice how perfectly the standard circuit symbol matches its function. Represented by this jagged zigzag line and marked with an R, a resistor doesn't store any energy for later. It merely dissipates it. When that electrical water pushes through the narrow pipe, it creates friction, releasing that energy harmlessly as heat.
Moving smoothly to our second concept, number 2, inductors, resisting current changes.
This is where it gets really fascinating. Inductance is the property of an element by which it opposes the change in the flow of current. Unlike the resistor that opposes the flow itself at all times, an inductor specifically fights against any sudden spikes or sudden drops. It essentially adds momentum to the current, wanting things to stay exactly as they are.
Drawn as a coiled wire, an inductor, which is labeled with an L, accomplishes the steadying effect in a very clever way. It temporarily stores electrical energy within a magnetic field. When the current tries to drop, the magnetic field actually collapses and pushes energy back in to keep it flowing. And when the current tries to spike, the field absorbs that extra push. It is literally the ultimate stabilizer.
Finally, let's look at our third foundational idea. Number 3, capacitors, opposing voltage changes.
If the inductor is a shock absorber for current, the capacitor acts like a tiny temporary storage tank within our network. While the inductor stabilizes the current, the capacitor's job is to stabilize the voltage. Capacitance is the property that opposes a change in voltage, resisting sudden electrical pressure spikes or pressure drops across the circuit. And the standard symbol perfectly mirrors the physical reality of the component. Those two parallel lines, marked with a C, actually represent its physical makeup: two parallel conducting plates separated by an insulator. Because the current can't simply flow straight through that gap, charges build up on the plates. So the capacitor stores its energy in an electric field rather than a magnetic one. It waits there, ready to release pressure the second the circuit needs it.
Now that we've deconstructed these 3 basic elements, let's look at finding circuit balance.
Let's step back and see how beautifully they balance each other out in a complete system. A core truth about all 3 of these components is that they're what we call passive elements. A passive element is a component that does not supply energy to the circuit. It only exists to either dissipate energy, like our heat-releasing resistor, or carefully store it, like our magnetic inductors and electric capacitors. They don't create power, guys. They manage it. This table brings all 3 concepts together, and a really calming reality emerges. No matter how terrifying or complex an engineering schematic looks, the entire physical network is just built from these 3 simple, manageable behaviors. It's literally just elements slowing down flow, elements smoothing out current, and elements smoothing out voltage. That's the whole shebang. Always remember this profound yet grounding thought: the energy may exist in many forms. Electrical circuits aren't magic, and they definitely aren't meant to be intimidating. They are simply highly controlled environments designed by humans to help energy safely change its form, doing useful work for us along the way.
So, the very next time you look at a tangled, intimidating circuit diagram, just remind yourself of this explainer. You already understand the physical reality of what is happening.
A peaceful, structured dance of energy being slowed, stored, and stabilized. The math comes later. But hey, here's something to ponder as you prepare to tackle those equations. If you now know exactly how to slow energy down and hold it in place, how would you combine these three simple pieces to make that energy oscillate back and forth, forever? Keep that question in the back of your mind, and you'll be perfectly ready for what comes next.